Welcome to week number 8. So the week 8 is about the halfway point of the semester after this week anyway. So reminder, homework 5 is due Wednesday. We'll talk about a lot of those problems today. I put up homework 6 a little earlier today, and it's due a week from Wednesday, so March 10th by 4:59 p.m. The reason it's 4:59 and not midnight is that's actually exam 2. So March 10th is the second exam. Okay, hopefully I've got the schedule right. I think that's good. We'll look at the syllabus in just a minute. Okay, so this week we are going to be kind of finishing up chapter 4, talking about chapter 25. So this second test will cover chapter 23 through 25. It's only 3 chapters, but there's a lot of material there. Series, parallel circuits, more complicated circuits, and then lots of magnetism stuff. Okay, so that's kind of the schedule. So this weekend I'll get a practice exam up. So next week, Monday, we will not meet in person because it's test week. But then Wednesday, we will meet in person on the 10th for the test. Okay? So I'll put up the practice test this weekend, then I'll make a practice test video. And then, make sure you look at both of those. And I'll give you some more information too. And then Wednesday will be in here for the test. So you make your own formula sheet, 1 page of a regular sheet of paper. Both sides, put whatever you want on there. Formulas, examples, words of encouragement, I always say that. Whatever you want. It's completely up to you. You get to keep that. Okay, any questions about the first 3 items up there? Now, as far as labs go, I put labs ... because we're kind of on a rotating schedule here. So last Tuesday, we M through P last names met in person, and then I put a pivot lab up for the other 2 groups to take a look at. Tomorrow, R through Z's will meet in person, and there'll be another online lab to do. Okay, so if you met in person last week, you'll have the choice of 2 labs to do. Basically, there's 3 labs for last week, this week, and next week. We're going to be doing them in different orders, though, depending on what your last name is. But in theory, there'll be 2 online labs up tomorrow. So if you did come in person last week, you have 2 to do over the next couple of weeks. You don't have to do them all in 1 week, but they're there for you anyway. So maybe you already came in person last week, but then you saw there was a pivot one, you decided to do that. You might have already done 2 labs. Okay, does that make sense? Okay, so R through Z's will meet tomorrow. Your official schedule says from 7 to 6:50 or 7 to 8:50. We're going to be meeting in room 220, which is actually across the hall. If you want to come at 5 o'clock, I'll be here at 5 o'clock. Usually the lab was at 5 o'clock. I'm not sure why they scheduled it at 7 o'clock this semester. Now, if you can't make it till 7, you've already planned on that. That's fine too. We'll still be here. But if you do want to come at 5 and you get a quicker start on it, you're welcome to do that. Okay? Okay, and then March 9th will be in person for A through L's, and then there'll be the 2 online labs still for the other groups to do. Okay, good. Any questions about the lab schedule? Yeah.
You said that we could show up at 5 to do the lab. Is that going to be the same for the March 9th session?
It will be, yeah. It's usually, I'm not sure why they put 7 to 8:50. I don't know if they made a mistake or what the reason was. But it'll be all the time whenever there's an in-person one. I'll be here at 5. Rick will be here at 5 probably. Okay, you're welcome. I know people have already made their work schedules and plans based on it being 7, so if you can't make it till 7, that's completely fine too. A side benefit of this is we're kind of more spread out then. The times are staggered. Okay, good. Maybe you can't come to the 5 o'clock one, but you don't want to wait till 7. You're free at 6:30. Just send me an email, so I'll make sure that I'm in that room. Because the 5 o'clock people will probably be done by 6, I would imagine. Okay, very good. Excellent. Good questions. So we've got a lot to wrap up with chapter 24 and talk about a little bit of new stuff. Oops. So I have on here kind of a summary of ways to produce a magnetic field. So we've got 3 different shapes. There's the long straight wire. So B stands for magnetic field. Mu 0 I divided by 2 pi r. So mu 0 is this constant that always appears with magnetism. There's the value of it. So mu 0 times I divided by 2 pi r. So if current is flowing this way through the wire, we can figure out the strength of the magnetic field a certain distance away, just called r. That's what the picture has here. This formula just tells you the strength of it. Which direction is it? Well, you've got to use the first right-hand rule. Put your thumb in the direction of the current, and then magnetic field loops around. So here at the top, it's coming out at you, and then down here, it's going back in. So this is a review. The second shape we had was a loop. Could be several loops, closely packed together. We can figure out the magnetic field right in the center. So for a center of a loop, mu 0 I times n. So I is the current, n is the amount of loops. If it's just one loop, then n is 1. If it's more, then it's whatever it turns out to be. Divided by 2 times r. So r is the radius of the circle, n is the number of loops. So that's the second shape. The third one is a solenoid. So a solenoid actually has some length to it. The difference between this and the loop, this is really tightly packed, really close together. This solenoid actually has some length to it. So we can calculate the magnetic field in the solenoid. So the formula is mu 0, same constant, times the amount of current, and then n divided by L. So n is the amount of turns or loops, whatever it says in the problem, and then L is the actual length. A lot of these solenoid problems, they'll give you the radius or the diameter. You don't need that. It doesn't depend on the radius or the diameter. Sometimes they'll give you n over L just as one number, the turns ratio, like 1,000 per meter or something like that. Sometimes they'll give it to you individually. 1,000 turns, the length is 1 meter, that sort of thing. Okay? So this chapter is really 2 parts. The first part is ways to produce magnetic fields, and then the second part is what happens to a moving charge in a magnetic field. So I thought we could, I'd give you a summary of this. We could do some problems related to this, and then we'll switch gears and go to forces on moving charges. So that's the plan. So I thought we could do some of these, look at some of these homework questions and use some of these formulas. So let me pull these up. Any questions on any of those, first of all? Okay. Okay. It's just taking a second to load. It's been very slow around here, internet-wise, today. All right, I'm going to actually try one more time, and if this doesn't work, then I'll have to go to a different browser. You believe spring break is already coming up? That's the week after test week. Okay. So an atom walks into a bar and sits down, and then the atom's looking around all over the place. And then the bartender says, "Did you lose something?" And the atom says, "Yeah, I think I lost an electron." And then the bartender says, "Are you sure?" And the atom says, "Yeah, I'm positive." Okay. If you can come up with a better electron joke, you're welcome to. Okay. All right, almost got it, I hope. Okay. Okay. For some reason, Chrome has been a little weird with mastering lately, at least for me. So let's see, we've got, this is the first one from the homework. Magnetic field at the center of a 0.7 centimeter diameter loop is 3 milliteslas. Okay, good. So Tesla, that's the unit of magnetic field strength. Okay, what is the current in the loop? So it's if it's a loop, immediately you should think, all right, what do I know about the loop? I showed you the formula earlier. So we want to calculate the amount of current that would produce this kind of magnetic field. And then the second part is a long straight wire carries the same current. What distance from a long straight wire would the magnetic field be 3 milliteslas? Okay, so this is kind of using two different formulas. This is just for a loop. And then this one is for a long straight wire. All right, let's take a look at this one. Okay, so for a loop, we had this mu0 I over 2r. Now you saw an n before, but n is just 1, so I didn't write the n here. So we want to know how much current is associated with a diameter of 0.7 centimeters. Be careful with the units. We want to put this into meters, so divide by 100, move it over a couple of spots. So 0.007 meters. And the magnetic field, 3 milliteslas. So that means times 10 to the minus third teslas. So that's what we know. And we're trying to figure out how much current is associated with both of those. Okay? Good. So if you really think about this formula, mu0 is just a constant, 2 is just an integer. There's only really 3 variables, b, I, and r. So they give us the diameter, but we could figure out the radius from that. Magnetic field's given. We just have to figure out what I is. So 2rb divided by mu0 would give us I. This actually is 2r, the diameter, right? Twice the radius is the diameter. So 0.007 meters, that's 2 times r. And then b is 3 milliteslas. And then you might have different numbers, so just be careful. And then u0, 1.26 to the minus 7th Tesla meters per amp. So you can see the answer is going to come out in amps, which it should. I forgot my calculator, so somebody will have to help me out with this one. What is it? Sorry. 16.667. Okay, good. So about 16.7 or so amps. Okay, that's the fourth. I believe the order of magnitude looks good on that one. 1, 2, 3, those cancel out. Well, let's see. Yeah, I think that might be okay. Anybody else get that? Yep. Yeah. Okay, excellent, good. Okay, so that's for the first part. That's how much current will produce that magnetic field at the center of the loop. And then the second part is, if you have a long straight wire with the same current that you found from this part, so a long straight wire with this current and same magnetic field, how far away from that wire do you have to be? So we won't put numbers in for this part, but here's the formula for a long straight wire. So using the same B and the same I, figure out how far you are away from the wire. That's what R is. So you have to do a little bit of algebra. Mu 0 I. So I'm going to put the R over here. So take this R, put it here, take the B and put it down there. As long as I did the algebra correct, we should have everything to put in this formula. And I think it looks good. Okay, so we won't do that number part, but that's the way to do it. Okay? All right, great. Any questions about this first one? Okay. Let's look at the next one. Okay, so here's a couple of wires. So consider the wires shown in the picture. The upper wire has 10 amps. What should the current in this one be so that the net magnetic field is 0? Oh, you can't see it. If I do that, just say, hey, I can't see it. Okay. So here's one wire carrying I1, which is 10 amps. Here's I2. We don't know how much current I2 has. We just know that the net magnetic field at this point is 0. So what does this current have to be in I2 so that the net magnetic field is 0? First of all, how could this even happen that it would be 0? We need a picture for this one. Okay, so we got I1 here going this way. It has its own magnetic field. Everywhere below I1, the magnetic field is into the page. Put your thumb in the direction of the current. Down here, magnetic field's into the page. Up here, it's out of the page. It loops around. So I1's magnetic field below I1 is into the page. And then we have I2 flowing the same direction. So let's look at the direction of I2's magnetic field up here. Same thing, you have to put your thumb in the direction of the current. So I can't do this really because the current's going the wrong way. So here's I2 going that way. So here the magnetic field, because of I2, is coming out at us. So this is in, this is out, they could actually cancel out. So in this area, I2's magnetic field's at you. Down here, I2's magnetic field's into the page. But between them, it's out at us. So that's how they could actually cancel out. So everywhere up here, that it's out at us. Okay? You can kind of guess if I1 is 10 amps, I2's current's going to have to be greater for them to cancel out. Why is that? Why would I2 have to be greater so the magnetic field cancels out here? No. Good, yeah, the distance away is farther. This distance is greater in the problem, so the current's going to have to be more so they can have the same magnetic field strength, just opposite directions. Good. Right, here's the picture. See, the point is closer to I1. So because I2 is farther away, its current's going to have to be greater, so the magnitudes are the same. Okay, so let's actually set this thing up. Okay, so let me just say like this one is equal to this one in magnitude. They're just opposite directions. So mu 0 I1 over 2 pi R1, and I'll tell you what all these are in just a minute. mu 0 I2 over 2 pi R2. So R1 in the problem is 1 centimeter, so 0.01 meters. That's the distance away in the formula, remember. And then this distance is twice as big. Okay? So you can almost guess if it's twice as far away, because of the way the formula is, the current is going to have to be twice as much. It turns out it is. You'll see that. Okay, so the mu zeros cancel out, the 2 pi's cancel out, and then I1 times R2 over R1 turns out to be I2 then. Whoops. Good. So that ratio is 2 to 1, so the current's got to be twice as big. Okay, good. Excellent. Any questions on that one? Okay, good. So the next one I just want to, without doing, just say something about it. Although the evidence is weak, there has been concern in recent years over possible health effects from the magnetic fields generated by transmission lines. A typical high voltage line is 20 meters off the ground and carries 200 amps. So estimate the magnetic field strength on the ground, and the answer is in microteslas. So we'll have to use something to calculate the magnetic field. We've got the 3 different shapes. Really the one that works is the long straight wire, right? So use a long straight wire and figure out the magnetic field that's 20 meters from it, that carries a current of 200 amps. Right, so mu 0 I over 2 pi R. The R is 20 meters, the current is 200 amps, and you can calculate the magnetic field at ground level because of this. And we'll see in the next chapter, maybe it's not so much the magnetic field, but a changing magnetic field that you should worry about. It turns out, and you'll see this in the next chapter, a changing magnetic field produces an electric field, and maybe that's what you have to worry about. But anyway, for this problem, just calculate the magnetic field, assuming it's a long straight wire. And then part B is compare it to how much the Earth's magnetic field is. Okay, so whatever you get, divided by the Earth's magnetic field, and they tell you it's 5 times 10 to the minus 5th. You'll see it's just a fraction of the Earth's magnetic field. So maybe if you're not worried about the Earth's magnetic field hurting you, you don't have to worry about this. Okay, that's the idea with that one. All right, let's look at the next one. Ooh, a solenoid. All right, so immediately from this chapter, the formulas are very specific. If it's a solenoid, you have the solenoid formula. Okay, is used to produce magnetic fields for research purposes. It is 1.9 meters long, inner radius of 28 centimeters, and 1,200 turns of wire. When the solenoid is when running, the solenoid produces 1.1 teslas, so that's a lot. Now, how much current does it carry in kiloamps? Okay, so this is an example of, they give you the radius, they throw a number out there. That just really describes the solenoid. It doesn't come into the formula for calculating the magnetic field at all. Okay, here they give us the turns and the length separately, which is no problem. Okay, so let's calculate this. So for a solenoid, you had this, mu 0 I N over L. Same thing I had before, just maybe written in a little bit different way. And here, what we're given is the length, 1.9 meters, 1,200 turns, and magnetic field strength of 1.1 teslas. And we're trying to figure out how much current. Yep. They also give you the radius, but we don't need that. So if I were doing the problem, say this were on a test and you were doing this problem, if you just wrote down what you have and what you're looking for, because you'd get partial credit on the test, you would get, if this were worth 10 points, you'd get 2 out of 10, just for kind of organizing your thoughts. You don't really need a picture with this one, but if you did, that would be, like maybe 3 points then. If you write down the right formula along with this, now you're up to like 5 or 6 points, right? You've got the correct concept, which is that formula, and you have the stuff that you know and what you're looking for. Okay, so I'm thinking about partial credit. Now we have to figure out how much current. So if you do the algebra right here, now you're up to like 7 out of 10. BL over mu0, let's see, looking for the current, mu0n. And then once you put the numbers in, get the correct answer, if you do that all right, you're up to 10 out of 10. This saves you from like, you accidentally write the wrong number down and you don't get any points. If there was a multiple choice test and you did everything right except for the last step, you would get literally no points if there were no partial credit. Here, if you just goof up a sign or something like that, maybe it's a point or 2 off, depending on how significant it is. Okay? So good, we have everything to calculate I then. So without putting in any numbers, this is the way to do it. Just be careful, they want the answer in kiloamps, so times 10 to the third. How many times 10 to the third amps do you have? Okay, great. Any questions on this one? All right, good. Let's say a couple of words about the next one. Oh, actually, we'll do this one. We didn't have time to do this one in the notes when we met last time. What is the magnetic field at the center of this loop? Well, we didn't have this shape yet, but we have a combination of shapes. The top part here is a long straight wire. The bottom part is just a loop. So pretend like the loop isn't here for a second. The long straight wire produces a magnetic field in the center of the loop. Pretend like the long straight wire is not there anymore. The loop by itself would produce a magnetic field at the center of the loop. So this one is to figure out the net magnetic field at the center. So we know how much current is flowing. We know the distance from the wire to the center. It's just the radius. This is actually the diameter, 2 centimeters. So do these magnetic fields, the one from the long straight wire and the one from the loop, do they work together or do they oppose each other? We'll have to check that out and see. So the current flows this way, back around, and then that way. So when it's going through the loop, it's going clockwise. So remember how to do this. Thumb in the direction of the current, magnetic field into the page. Now for the long straight wire part, same idea, thumb in the direction of the current, magnetic field into the page. Okay, so they actually add together in this problem. So we'll have to add both of those contributions together. Okay, so let's do that. Any questions about the setup of it? And the point we're looking for is right here, 1 centimeter from the long straight wire. Okay. So the net amount is the magnetic field from the long straight wire plus the magnetic field because of the loop. So for the long straight wire, we have mu0 I over 2 pi r plus mu0 I over 2r. So this is the long straight wire, this is the loop. And then r, the radius of the circle is the same thing as the distance from the wire to the point. So the diameter of the loop was 2 centimeters. So this is 1 centimeter, or, divide by 100, 0.01 meters. Okay, and it's the same current that flows in the loop and the wire. It's just bent into that shape. So 5 amps. Okay, same thing. This is just the current. Excellent. So without putting in the numbers, this is the way to get the net magnetic field. Okay. Any questions on that one? It's kind of fun with magnetism. You can put things into different shapes and get different magnetic fields. All right, so let's look at one more with this producing magnetic field idea. And this one, we'll just talk about this one. Oh. Good. Experimental tests have shown that hammerhead sharks can detect magnetic fields. In one test, 100 turns of wire were wrapped around a 1 meter diameter cylindrical shark tank. Okay, so it's like, a circle, but it's a cylinder, so it's got some shape this way. And the diameter is 7 meters. Okay, good. A magnetic field was created inside the tank when the coil of wires carried 1.5 amps. Sharks trained by getting food as a reward when the field was present. Sharks trained by getting a food reward when the field was present would later respond when the field was turned on. Okay, so basically they're turning on a magnetic field stimulating sharks, and they would give them a treat, basically. So we want to know what was the magnetic field strength in the center of the tank due to the current in the coil. Okay, so this is just like a loop, and we can figure out the magnetic field right at the center. Okay, so the center of the tank. So they're kind of playing around with the sharks by turning on the current, producing a magnetic field. The hammerhead sharks detect it, and they get a treat when they detect it. So we want to figure out the magnetic field because of a loop with 100 turns. So this is a loop problem. So I don't want to put the numbers in, but just remind you what that formula is. So for a loop, we had mu0 I, the amount of turns, divided by 2 times R. So in this problem, we're trying to figure out B, and we know the current is 1.5 amps. N is the amount of turns, so 100. And then this would be the radius. They actually give you the diameter, so the radius is half that. And then we want to figure out B. Okay, and the second part is it larger or smaller than the Earth's magnetic field? So here's how to calculate it, and then you can compare it to the Earth's magnetic field. So the Earth's magnetic field was this, given in the book. Okay, good. As a human, it would be neat to be able to do that, Somebody turns on a magnetic field and you can just sense it somehow. Okay, very good. All right, good. Any questions on this one? Yeah. No, see, that's the thing about this. Yeah, how do we know to use the loop? So when I'm reading this, I know it's not a long straight wire, so the choices are between, is it a solenoid or is it some kind of loop, So to be able to do the problem as a solenoid, they would have had to have told you like the depth of the pool. So for that reason, I'm just assuming that it was a loop. Yeah, that's they could have made it better. Like assume this is a loop and not a solenoid. Yeah. Yeah, that's exactly right. It's kind of they could have done a better job with directing you towards the fact that they want you to use the loop formula. Okay, yeah, great. Excellent. So the other part of the chapter is we've seen several situations where you could produce a magnetic field. What happens to a moving charge in a magnetic field? Okay, let's see. This is too high. So here's the formula. The force on a charge moving in a magnetic field. I made a video last week, like part 2 of chapter 24. This information is there. The force is given by that formula up there. Q VB sine of alpha, and then alpha is the angle between V and B. So if V and B are lined up with each other, you're moving that way, the magnetic field is that way, there's no angle between V and B, there is no force. You have to have part of the velocity perpendicular to the magnetic field, or there's no force at all. The direction of the force you get from the second right-hand rule. So let me show you slide 105 of the notes. So here's the magnitude of the force. Here's how you've got to line these things up. So V goes on your thumb. You can write this on your hand if you want to before the test. V, B is your pointer finger, and then F is the force. Make sure you use your right hand. So the force is always perpendicular to the plane made by V and B. So here's V, here's B. The force is always perpendicular to V and B. V and B don't always have to be perpendicular to each other, though. V and B could be at some kind of angle. The force is a maximum when V and B are perpendicular. When they're lined up with each other, the force is actually nothing. So as long as there's some angle between V and B, you have a force. And it's always perpendicular to the plane made by V and B. Okay, so if V is like this, B is like that, the force is out at you. So no matter where I put my thumb here, as long as it's not zero, the force is out at you. That's for a positive charge. For a negative charge, the force just goes the opposite direction. So what they do in the book, and most books do this, figure out the direction of the force on a positive charge. A negative charge, the force would just be the other way. When you're really advanced, you could use the left-hand rule for negative charges, but let's just stick with the right-hand rule for now. Okay, so the speed is meters per second, B is in Teslas, the charge is just in coulombs, and then we can figure out the force then from that. Okay? Good. So we can do several different things with this idea. Let's look at a couple of problems first of all, though. So what is the magnitude of the magnetic force in figure A? Whoops. And then what's the direction? Same thing in these other parts. So you really have to start thinking in 3 dimensions here. So this is in 3 dimensions. This is X. Y is sort of into the page, and there is Z, right? Okay. This is the negative X-axis, negative Z-axis. The negative Y-axis is out at you. So I'm looking at figure A and figure B. Let's do B first because it's actually easier. No part of V is perpendicular to B here. V is going this way, B is going that way. There's 180 between them. The sine of 180 turns out to be 0. Another way of thinking about it is no part of the velocity is perpendicular to B. So the answer for B is 0. There is no magnetic force. So if you go this way, or if you go this way, a moving charge in a magnetic field does not experience a force. So B is actually the easier one to do. Okay, any questions about B before we go back to A? Okay, so in A, we have V here. Oh, it's a proton, so it's positively charged. Here's the speed, 1 times 10 to the 7th. And the magnetic field strength is given. Okay, what's the magnitude of the force? Okay, so here's V, here's B, so it's 45 degrees between V and B. Okay, so we can use the formula that we had. So remember, if you forget the formula and you're working on this, and you don't want to look in the book, you could just hit review. And this takes you to the part of the book that you need. There's the author. So you can thumb through here, get to the formula. So Q, given in the problem, V is given, B is given, and then alpha is the sine of the angle. Alpha is the angle between V and B. So in the problem, that's the angle that we need, 45 degrees. Okay, so QVB sine of 45, that'll give you the force. Any questions about getting the magnitude? Now, how do we get the direction? That's what part B is. Is it the plus x, plus y, plus xy, etc. direction? So you've got to line these things up. To get the direction, you need the second right-hand rule. Okay, so here's where V is. Here's B. So the force would be into the page, which in this picture is the plus y direction, right? So I'm lining them all up. V and B are free to move. F is always perpendicular to the plane made by V and B. So V and B, force would be into the page. I can't do it this way, right? I mean, I could try to do something, distort myself. That's why I'm coming over.
So at this point, the audio went out, so I'm just going to be narrating this. So as you can see, I'm lining up my thumb with V, my pointer finger was with B, and then the force was into the page for that one. So on your fingers, remember your thumb is the velocity, pointer finger is B, and then your other fingers are the direction of the force. Okay. And then here's the next problem. It's a similar problem. You can see V is coming out at you. B was along the x-axis. And electron speed 2.5 times 10 to the 7th. So it's an electron. You know the magnitude of the charge, 1.6 to the minus 19th coulombs. You know V, given in the problem, and B is also given in the problem. Okay. So we'll have to look at the picture in just a second to see the angle between V and B. And then it's sort of like the last problem where we can use V and B and the angle between. And then again, electrons, so you know the magnitude of the charge. Okay? And that's just going back to the last problem. Okay, now we're back to here. So you can see V and B are 90 degrees to each other. So 90 degrees, sine of 90 is 1. So this is the situation where the force will actually be the greatest. And then we can figure out the direction of the force using the second right-hand rule. Just remember, this is an electron, so whatever you get for that force, the answer is going to actually be the opposite. Okay, so I'm probably saying something similar to that in class. And then that's 90 degrees. I'm pointing out that V and B are 90 degrees to each other here. Okay. So there I am lining everything up. V is where your thumb goes, B where your pointer fingers are, and then the force is the direction of your other fingers. So the force is always perpendicular to the plane that's made by V and B. It's kind of hard to do it in that picture, so I think what I'm about to do is show you another way of looking at this. In that picture, you're trying to look at 3 dimensions on just a flat sheet, and it's hard to do that. Okay, so here's a piece of paper I'm about to write on, and this is just another way of representing this. So there is V coming out of the page. So this is the same thing, and just I'm just drawing it up in a different way. There is B that direction. Now it's easier to actually line these things up. So V, as you can see, that's where your thumb is, out of the page. So 3 dimensions, left, right, up and down, and then in and out. So you got 3 different ways of looking at it. All right, so there's V coming out at you. There's B to the right. So the force would be up, but it's a negative charge. So the force is down. Okay, and you'll have to reconcile that with the picture that you had to know what direction is down in this picture. This way of representing it. V out at you, B to the right. You could figure out the direction of the force. On a positive charge, it would be up. So a negative charge, it's down. Okay, let's head back to the problem. That's what I'm doing in class, switching the view from the document camera back to the actual problem. Okay. So in this problem, they give you an angle of 45 degrees, but is that really the angle that you need for the formula? We need the angle between V and B. So V and B are still 90 degrees to each other. The angle between the y, really the negative y-axis, and V is 45 degrees, but it's in that plane, that YZ plane, which is perpendicular to X. So the angle between V and B is still 90 degrees. So the magnitude of the force is still going to be the same in part C. Now the direction, though, that's where the angle comes into play. The direction of the force is perpendicular to the plane made by V and B. So you'll have to really think about this one. Which direction is the force? And again, you've got to think in 3 dimensions. Okay, let's see what's going on here. Okay, so going on to the next problem, I need to show you a little bit about something called a flow meter. So this is a magnetic flow meter. So charges are moving to the right in the picture, positive and negative charges. This could be blood, like calcium and sodium ions moving to the right. They're charged, they are moving, there's an external magnetic field going from north to south. So charges in an external magnetic field experience a force. So basically what happens is, in this picture, positive charges move to the inner part of the canal that you see. Their negative charges move to the outer part, and there'll be a better picture in just a minute. And when you got a separation of charges, you have a voltage. So I'm explaining now that the charges are moving to the right. The magnetic field is down, so the inner part becomes positively charged. That's my left hand, and the outer part, my right hand, becomes negatively charged. And then there's an electric field across there and a potential difference. So depending on how fast these ions are moving, we get more and more, on one side positive, one side negative, so the voltage gets larger. So what you can actually do is measure the voltage, and that's proportional to how fast the ions are actually moving. There's one of the homework questions that deal with this problem. So here's a view, an end view. So here the charges are coming out at you. I'll let myself line it up. Charges are coming out at you. That's from where the thumb is. Magnetic field's down, so the force, magnetic field down, so the force on positive charges would make them go to the right-hand side, force on negative charges to the left-hand side, and then we have a separation of charges. So we have a potential difference that's set up. We could measure the potential difference, and that's proportional to the voltage. So then if this were an artery or something like that, you could measure the voltage, and then from that figure out how fast ions are actually moving. So with this magnetic flow meter, the magnet part would actually be built into it. You wouldn't have a separate bar magnet on the top and bottom. It would be completely built into the device. Okay, so just put a couple of leads across this blood vessel, or it doesn't have to be blood, it could be anything with a charged fluid, and you can then measure the voltage and figure out how fast things are moving. So one of the homework questions again deal with this. I think we're about to take a look at that. Okay, good. So we have an electromagnetic flow meter, applies a magnetic field of 0.2 Teslas to blood flowing through the coronary artery with the speed of 15 centimeters per second. So be careful, that's centimeters per second. We will have to change that to meters per second. And we just want to know, it looks like, what force is felt by, I'll have to wait until the camera moves over. So what force is felt by a chlorine ion which has a single negative charge? Okay, so the magnitude of the charge, 1.6 to the minus 19th coulombs. Okay, so we're going to assume that the magnetic field is actually perpendicular to the direction that the chlorine ion is moving. So the angle between V and B would be 90 degrees there. And then it's sort of a straightforward application of this formula. So this is, again, another application of this idea of electric force, or sorry, magnetic force on a moving charge. Okay, so QVB, and it's a sine of 90. And the Q that you use again is 1.6 to the minus 19th. Okay, so here's a picture of what the flow meter actually might look like. Here's some ions moving that way. In my picture, I've got the magnetic field going into the page. So moving to the right, magnetic field into the page, the force would move positive ions to the top, as I'm showing there. Negative ions then go to the bottom, and then you have a potential difference across there. You get to the point where the magnetic force, that's what I'm writing now, is equal to the electric force. Right? So a positive charge from the magnetic force would move to the top, but then because there's a bunch of positives on the top, then there's an electric force the other direction. You get to the point where those are equal to each other. So Q times the velocity times B is equal to Q times E. The Q's actually cancel out. Going back to a previous chapter, we knew delta V is equal to ED, so we could take that and plug it in for E. You don't measure the electric field directly, you measure the voltage. That's what we use the meters for. Okay, so finally you see the relationship. Velocity times magnetic field is equal to delta V divided by D. A little bit of algebra and you come up with the formula. Knowing the magnetic field and how thick this blood vessel is, and measuring the voltage, then you can come up with the speed. So you don't have to cut into the artery. You could measure this, well, you've got to cut into the body, I suppose, to get to the artery. But then you don't have to insert any kind of little meter inside of the artery. They probably are really small, right? So you can measure how fast blood's flowing just by measuring the voltage and knowing the magnetic field and maybe estimating how thick the vessel is. Okay. So that's probably what I'm saying there. Any questions? No. Okay, let's move on. Okay. So I'm saying that this is another application or phenomenon that occurs with magnetic force. And I think what I was talking about was the northern lights there, where the force is QVB. The Earth's magnetic field is got a part perpendicular to the flow of particles coming from the sun, and then you see the northern lights appear when okay, so here we go with it looks like we have an electric field and a magnetic field that are set up here. So this is something called a velocity selector. So the magnetic field and the electric field are going to be equal to each other. So only particles with a certain velocity are going to be able to go right through this. This is another application of this idea of magnetic force. So we want to pick out certain ions that have a certain speed. Those are going to go right through. Anything else will not make it through. So this is used in a lot of different research if you want to pick out an ion that has a certain speed. So this is called an E cross B field. So particles move to the right. You'd have an actual plate there and a plate here. And then only charged particles with a certain speed could make it through there. The other ones would be blocked. Some of them would maybe head up here. Other ones would head down there. Only a certain speed makes it through. So what is that speed exactly? Well, we can figure out what that speed is. And we'll do that here in just a second. So magnetic force, QVB, is equal to QE. Really, it's the magnitude of the charge, but it cancels out anyway. So whenever the speed is E divided by B, particles will make it directly right through. If not, they either land at the top or the bottom, hit the screen. Only those certain speeds are the ones that make it right through. Okay, there's a couple of, maybe one homework question on this, and also couple of other applications of this in the homework. We'll see that here in just a second. Which I believe that's what I'm doing now, changing the screen to that screen. Okay. And here we go, finally. An electron travels with a certain speed, and it's an electron again, so you know the magnitude of the charge, between two parallel plates. So that's like a capacitor. We got an electric field set up. The plates are separated by 1 centimeter and charged to 200 volts. What magnetic field strength will allow the electron to go directly right through? This is a velocity selector. Okay, so I'm reading the problem there. So we know the speed. Now you know the voltage and the plate separation. We have a relationship between electric field, voltage, and separation, if you remember. So I'm probably walking over there now and going to show you that. Okay, so the voltage is E times D. So we don't know the electric field directly, but we know the voltage and we know the plate separation, so you can figure out what the electric field is. Just be careful with the units. So you can take that and plug it in for E. Then the only thing that you don't know is B. That's what you're trying to find. So delta V, be careful, good, 0.01 meters. The speed's actually given in the problem as well. 1.1 times 10 to the 7th, it looks like, meters per second, so well below the speed of light. So we can figure out the magnetic field part then. So doing a little bit of algebra, B is equal to E divided by the velocity. If you want to, you can plug in delta V over D for E. So just be careful. Delta V, the big V, is the voltage. The little v is the velocity. Okay? Very good. Any questions? I probably said. Okay, so we got B. We have B is equal to E over V, but E is delta V over D, and I plugged that in to come up with that formula finally. Okay, good. So these units are a little weird if you look at them. Like you got magnetic field, you got speed, you got electric field, voltage. So what I'm doing now is just showing you how all the units relate to each other. So F is equal to QVB. The units of force are newtons. The unit of charge is coulomb. The unit of velocity is meters per second. The unit of magnetic field is teslas. So I just want to show you how all these are related to each other and why. So Newton, I'm just rewriting this, coulomb per second, meter times Tesla. But a coulomb per second, I just asked the class this question, what is a coulomb per second? So if you think back to a previous chapter when we started talking about current, a coulomb per second is an amp. So that's just another way of thinking about all this. You can get lost in the units really easily. So a coulomb per second is an amp, and then we still have a meter times a Tesla. So a Tesla is a Newton per amp meter. But just don't forget what an amp is, a coulomb per second. So that's how they all relate to each other. Okay, good. So that's a little bit of a comfort level, hopefully, when you see this. You have a way of going from different units to different units. Like, for example, newtons are force, Tesla's magnetic field, amps are, from electricity, so that's how they're all related to each other. Okay, so you can keep that in your mind. If you get an answer and you're wondering, does it even make sense? These units are seem to be a mixture of different types of units, but there is a way that they're related to each other. Okay, good. So I'm going back to put on the either the PowerPoint or another homework question here. Let's see what it is. Okay, so a Tesla is a Newton per amp meter. Okay, so this is one of the homework questions from homework 5. So this is a way of building a mass spectrometer. Actually, there's several different varieties of mass spectrometers. This is one that uses a magnetic field. So in the picture, if you can see it, and you've got your homework, you can take a look at it if you can't quite read what this says. Atoms enter at the top there, and then they hit a magnetic field. The magnetic field is out at you in the picture, and they follow that curved path. So for a given speed, more massive particles are going to follow a larger path. They follow a circular path, the reason being the magnetic force is always perpendicular to the way this is traveling. So let's take a look at this. You have a sample of unknown composition. First step of analysis might be determination of the masses of the atoms and molecules in a sample. So a mass spectrometer, to make such an analysis, can take various forms, but here's one. So for many years, the best technique was to determine the masses of ionized samples using this, and this is still used. The lab that I worked at when I was getting my PhD at Purdue Rare Isotope Measuring Lab, uses this, and it's really the most sensitive, really I think probably in the world still. It could detect one particle in 10 to the 15th. So it's literally like finding a needle in a haystack, using several of these actually. Okay, so let's see the direction of the force on a charged particle. So we know the direction of the velocity. Okay, so the velocity just follows the path there. So actually the velocity technically is tangent to the path. So what I'm showing you is the direction of the velocity. So the velocity is down. The magnetic field is out at you. So the force is to the left. And what I'm talking about is the point right. I'll show you in just a second. Right there, that point there. The speed is down, the magnetic field's out at you, so the force is towards the center. So this must be a positively charged ion for this to happen. A negatively charged ion would actually follow that path, and that's probably what I just said. Okay, so the path that we see here works for a positively charged ion. So at that point, V is down, B is out at you, so then the force is towards the center of that circle. Okay, so that'll give you the direction, and then you'd have a detector down there. Anything with a certain mass, anything with a certain mass would follow a certain radius and hit the detector. It's charged, so the detector reads how much current you have. A certain amount of charged particles hitting this detector would give you a certain amount of current, and that's proportional to how many ionized parts of your sample actually hit there. Here's the next problem. This is a similar problem. It's just trying to figure out the radius for this. What will the appropriate distance between the points be? Actually, it's 2 times the radius if you look at the picture. So we can figure out the radius, and then they're actually asking for 2r, the distance between the part where you go in to the part where you come out, and only certain masses, again, will make this trip. Okay, and again, the detector there only detects things that actually hit it. It's charged. The detectors are built to register a current. Okay, so it looks like we're going to take a look at some numbers for this problem. Okay, so you have to think back to circular motion from Physics 220. Whenever you go in a circle, there has to be a force towards the center. Okay, so F is equal to ma, Newton's second law. The only thing is it's a special kind of a here. It's the radial acceleration, and that's mv squared over r. Okay, and then what is the actual force towards the center? It's the magnetic force, which is QVB. So one of the V's actually cancels out. So we'll use that. One of the V's will be canceling out. We have mv over r is equal to Q times B. It's just the magnitude of the charge there too. So the book solves for the radius, mv over QB. That's the radius that the particle will follow. So if you know the mass and the speed, the charge, magnetic field, you can calculate the radius. So if everything has the same charge and the same speed because you've used the velocity selector, same magnetic field, different radii will correspond to different masses. And that's probably what I'm saying there. So in the problem, I believe they tell you the charge, the magnetic field, they tell you the mass in terms of the mass of a proton, and also the speed. So remember, it's we'll go back to the problem, but the mass of a proton is 1.673 times 10 to the minus 27th kilograms, and you'll need that information to solve this problem, as we'll see here in just a second. Okay, so there we go. The magnetic field strength in my problem is 0.8. The speed also given, 2.3 times 10 to the 5th. And the molecule has a mass of 340 times the mass of a proton. So it's 340 times 1.673 to the minus 27th. And it says they're singly ionized. That means they have a magnitude of charge of 1.6 to the minus 19th coulombs. Okay, good. So you'll have to put all that together to figure out the radius, and it's in centimeters. So this is a problem that you might see on an MCAT if you're going to be taking the MCAT. I believe it's to get into medical school. I don't think you can use a calculator on the MCAT. At least you weren't able to before. So hopefully these numbers that you put together work out pretty well. And you can try doing this without a calculator and see what you come up with just for practice. And then just remember it's in centimeters. And I think that's probably what I'm saying right there. Okay, very good. So if you ever go to the study area on Mastering Physics, there's some practice MCAT tests. So if you are going to take the MCAT, that comes with the book. You can take a look at those when you get a chance. I know everybody's busy with other things, but maybe if you find yourself with a few minutes, you can take a look at that. Okay. And that's sort of what I'm describing there about the MCAT and putting in, doing this in your head, because you won't have a calculator in an MCAT. That's just for people that are going to be, trying to get into medical school. Okay. There is one other thing to talk about in this chapter. It's the, and I'll do it here in just a second. It's the force on a wire. And here's the formula for it. You're about to see. So current moving through a wire, those are moving charges, right? So charges are moving through a wire. They're in an external magnetic field. They're going to experience a force. So on this slide, I'm just giving you the formula. Now the way to think about it is what we have from before. Force is QVB. So the Q part is in coulombs. The V is meters per second. and then you still have B. So coulombs per second is an amp. That's where the current part comes from. You still have a meter left over. That's where the length part comes from. And then B is still there. And then it's still the angle between the current, which is flowing through the wire, and the magnetic field. Okay, so the direction of the current and the magnetic field, the angle between those is the angle alpha, just like we had before when we looked at QVB sine of alpha. Okay, so without a rigorous derivation of this, I just sort of talked about the units and how the units work out. So current, coulombs per second times a meter, so really you then have a coulomb, meter per second. The coulomb part, that's where the charge comes into play, and then the meters per second, that's where the velocity was from. So this is a bulk way of looking at this. So ILB when the angle is 90 degrees. This is the basis for a motor. So with the motor, you supply the electricity in a wire. It's in an external magnetic field. The wire experiences a force and it moves. So if you have any kind of electric motor that you use, maybe I think I said if you drove your Tesla to class that day, you maybe use an electric motor and you use this idea where you supply the current, or a battery supplies the current. You're in an external magnetic field and you experience a force. Okay? Very good. And that's where class basically ended then. Okay.